just saying there is only so much you can say about a library, okay? Generally, here it is, this is what it is. So what I plan on doing was to go over the overview of IPP, exactly what it is. I'll then relate it to the kind of hardware platforms you can run it on. I'll then be looking at not in too close to detail, but some of the syntax for the calls, and also a sample pseudocode example of how you might implement it with a signal processing kind of thing. I'll also then relate it to OpenCV and then also to the MKL, okay? Because there is considerable overlap between the various systems. Okay, so IPP, what is it and why would you want to use it? It is a very large library of functions. As I understand it, they're all hand-coded, so they're all written in assembler. They're developed specifically to make use of hardware on the modern Core Atom Xeon chipsets. So it's got functionality designed into it to take advantage of the vector operations. It's also there to allow you to help develop multimedia data processing applications. This is where it's kind of slightly different from the MKL, because the MKL is a much higher level set of library communications, library functions. Also, you can use it for communications. It's also ready to use royalty-free. That means that once you've built an application, then you should be able to just allow the runtime library to go out with the application itself. So there's no further costs. It comes with Parallel Studio. It also comes with a couple of other Service Studio and native developer environments. But I'll be talking about that a little bit later, and that's where some of the repetition is going to come in. It's highly operated for the SSE and the AVX architectures, as I said. So, I mean, Intel are trying to push certainly the AVX architectures, and they're trying to make these programs kind of bulletproof for the future. Okay, so essentially the operating systems you can run on, the usual kind of culprits. It's Windows, Linux, Android, and OS X. There's another one, which I've forgotten for the time being. It is compatible with other compiler systems, providing they've adopted the same kind of standards. If they haven't, then obviously it's not going to work. The one major difference between IPP and MKL, the math kernel library, is that IPP is for C++ and C only. So that's, to my mind, that's somewhat of a limitation. I have seen some chatter on the web about Fortran bindings, but I haven't seen any particular implementations of that yet. Okay, so the system requirements just go straight to the website. As I said, it's validated for use against Intel Xeons, Intel Core, that's typically the i3, i5, i7, the Xeon Phi, the Intel Atom, and, that was the other processor, I couldn't remember. So it will run on all of those things. The structure of IPP is that if you've got one of these processors, then you can run on it. If you haven't got one of these processors, software takes over, and the code is then implemented in the software. Obviously, it's going to be a lot slower, but you know it's there. So you've got a certain level of portability across these platforms. If you go to the website and look for IPP, I suggest you be very careful, because there's a lot of archive material, legacy material on the website relating to previous versions. Intel are currently only supporting, and I don't think they'll go back to any other releases whatsoever, 8.2 updates 1 and 2. Okay, and the reason for that is there will be massive changes internally and externally on the API. Also, there are a whole bunch of, they call them domains, essentially. They're all meant to be part of this IPP thing, which again I'll come into a little bit further in a little while. But these have actually already been marked for deprecation, so in future releases they won't be actually in the IPP. That's not to say that they won't necessarily exist somewhere as a library, but they won't automatically come in as part of the IPP set. Okay, so a horrible light blue, as I say, where you can find it. It's definitely part of the parallel studio, the system studio, and the integrated native developer stuff. There is one thing, I thought this was wrong, but I checked this morning, and I'm pretty certain this is actually right. There is no standalone package. You need to have one of those tools, tool sets. Okay, so as I said, it's cross-platform. Okay, we've just been through that. VxWorks, that was the other one I was trying to think of. VxWorks is an embedded operating system, so you can actually get direct access to a kernel and user memory, as I recall. It's got various other platforms you can work on, obviously the phones, tablets. What is an IoT? Any idea? No? Well, let's skip that one then.
Wait a minute. Internet of Things.
Oh, is it?
Yeah.
Okay.
So that'll be something you plug in at home or something.
Oh, right, okay. Yeah, I didn't recognize it, but I thought I'd just leave it in just in case. So the main feature that I want to point out on this side here is that it is really only for C and C++. Okay, and it does target explicitly the CPU you're running on, which relates back down to the optimization goals, because it's all about performance, platform throughput, and power efficiency, which is another interesting thing. If you run the vector units on the processors for too long, they'll get too hot and kick out the machine. There's the features which are very much different from the previous versions are the dispatcher. Of course, you've got static and dynamic libraries. Now, it's these two things here that are the major difference between the previous versions. Okay, so what happens here is that the dispatcher is the one that selects what hardware you're running on, whether it's a core or a Xeon or whatever, whether you're running with an SSE or an AVX type architecture. This is the kernel mode. Kernel mode ready is where you can actually access the user and kernel space. Yeah, so this is actually the big ones, that one and that one. So we'll talk about that in just a minute. Oh, the libraries. That one, the cryptography one, has got an asterisk against to go. I'd say so are those, but that's because I think it's something to do with the American legal system and their munitions laws or something. So it's only available, may only be available in certain geographies. Okay, again, the domain areas are signal processing, image, computer vision, string data, and cryptography. So what this does is that actually, what they've tried to do is create a library whereby you can actually select the bit depth for the application. So you've got some level of reusability of the calls. So yeah, so the example I've got coming up is the signal processing one, which is the one-dimensional input data processing. So that would be what's known as a finite impulse response filter. And again, a similar kind of map of the various bits and pieces, what they're used for. The left-hand side column is pretty much the same as the right-hand column. So you have essentially a very small number of IPP core primitives, and then you've got much larger libraries for the maths and signal processing. Okay, and of course they have applications in image and computer vision and data compression. I'm not quite sure why the math vector library would have anything to do with string processing, but hey, what the hell. Okay, so actually there are 3,500, I didn't realize that, there's much more than 2,000 then, primitives in the image processing library. And obviously they've got the various applications. As I said, there would be some replication of slides. Again, platforms, the various ones we just talked about. And of course, the little Xeon Phi, that's only just begun to start to happen for the Xeon Phi, I suspect. I think we were running them in Munich quite recently, but I think it's still a work in progress. And of course, you've then got the various operating systems you can run with. Okay, the dispatching model. The next slide will actually explain these things, and what they stand for. Okay, I've just thrown it in for completeness because at some point this will go on a website or something. So I just thought, well, if it's there, people can have a quick gander and see what they actually do. So with this system, you need to initialize the system in some fashion. Once you've done that, this is a copy. I think this is an image copy. And what it then does is it decides which platform you're running on. And apparently it takes about 10 CPU clock cycles to actually do this. And once it's decided what you're running on, it will then choose the appropriate library from the merged libraries to pick up the right command and go off and do the copy itself. Again, it's kind of dependent upon things like bit depth and all that kind of stuff. So I'm not going to go through these. All these codes are the beginning. If you've got the beginning of these things, okay, that's all it says. So PX is generic code optimized for processors with Intel streaming, so that's SSE. You've then obviously got variants on that, SSE2, SSE3, and then coming on down to the AVX ones, which are the G9 and E9. Okay. SSE4. Does that exist? Don't know. Okay, the data types. This is a slightly technical side. Again, I'm going to pretty much skip over this fairly rapidly. All the types, obviously every package has got its own type structure. All the types begin with IPP. Then you've got a number denoting how many bits are involved, and then whether it's signed, unsigned, whether it's floating, or whether it's complex. If you want higher complex numbers, I mean, this is the way they create it according to the website. There is actually one thing that's actually concerned me about this is whether they've actually managed to enforce data alignment or not. I would have thought, in all honesty, if they're trying to make use of AVX or SSE, then they need to have data alignment as being an important feature. So that's the data types. Now, the next one is briefly going over the actual function call. The function calls all start with IPP lowercase, I think. I've got an example in a minute. Then you've got a domain name. The domain names are related here, signal processing or matrix operations, or image and processing. So that tells you exactly what the system is, what the program is meant to be doing. Then you have some kind of name. Say, for instance, it's part of your FIR library or whatever. You then have your data type, which is your bit depth. Okay, again, whether you're dealing with 1-bit, 8-bit, 16-bit, 32 or 64-bit systems. And of course, then you've got another descriptor, which could be, say, like init, for instance. So you're initializing the system. and then you've got a list of parameters. So that's essentially the call structure. And I've got 3 of these, and I've got them in for a reason. Because the example I want to show is a simple FIR case. Are you familiar with what an FIR is? Ah, all right, okay. An FIR is a weighted average, okay, where the weights of you take a signal, and you've got a small window of what's known as taps, and essentially it's a series of numbers that you multiply to the first vector, and you sum them up, and it's the weighted average, and then you just progress through the larger vector, which is the signal. Okay. This actually, I was going to try and give an example of that, but this I don't think will work with my stuff because the IPP is designed for small data sets, not large ones, and my data sets are actually quite large. So, okay, so. Okay, yeah, so we've got IPP status. That's going to be obviously a return of whether it's done the right kind of thing or not. And what I'll do, by the way, is then contrast this to what happened previously with the older versions and see why there's so much difference. Okay, it's part of the FIR package. It's going to be dealing with single floating point numbers. And this is going to get the size of the system by calculating. So it's got the tap length, it's got the tap type. That's to say it's going to be 8-bit, 16-bit, or whatever, and then it just works out the appropriate sizes for the various buffers. But it does not allocate any buffers. So this is the length of the filter, bit mask field, pointer to the size of the internal. Oh, sorry, yeah, the pointer to the inside of the internal constant. Structure, specification structure, and all that does is it keeps an idea of pointed material, but it doesn't actually allocate the stuff itself. Okay, so it's much more lightweight. And then, of course, you might want to have a work buffer, so pointed to the size of the buffer you want to actually use. So the first step in this is to get the size of the things. Okay. A subsequent call then will be to initialize things, in which case you need to put a pointer into the filter coefficients. That's the weighted averages. Sorry, the weights rather, and the length of the FIR. Again, the bit field mask, and then pointed again to the internal specification structure. That just keeps information about information. That's almost like your metadata level. And then, rather messily, you actually perform the actual signal processing itself. Okay, so you need a pointer to the actual source vector. That's your signal. In my case, that's a reflected radio signals off meteors and atmospheric meteors. A pointer to the destination vector. You can do this in place or out of place. I was looking at the code this morning. The number of elements in the destination vector, which doesn't necessarily have to be the same, or isn't necessarily the same as the number of points in the source vector, because you need, if it's the same number, then you actually need some extra padding to go on the end of the source vector. There are 2 here that I don't know what they do. That's those 2, so I'm not going to talk about those at all. Again, the internal specification structure, and then you have a pointer to a work buffer. So those are the 3 operations you need to go through with the FIR, and I think okay, yeah. So, oops, where's that gone? Ah, yeah. So the reason there's so much difference between these things, and okay, this isn't actually as clear as it could be, but these are the three functions we've just had a look at. These are the old versions, okay, and there are no pointers there as such. So memory has actually been allocated on the inside of the routines, which can cause problems for thread safeness and memory leakage. Okay, so now at this point, So this would be pre-8.2 or pre-8, and this is now 8.2 plus. So the user is now responsible for declaring arrays, cleaning up after them, and passing arrays in for processing. Okay, but here the system is actually doing it for you. So and that's the massive change that's happened, that they've gone away from this paradigm down to this paradigm. So if your code leaks, it's your problem. Again, a difference between the structures. I think only the two top blue ones are of any interest, really. You would have, in the old systems, you would have a state, a structure, whatever. That would be essentially the equivalent of your specification structure. Then you'd have to allocate memory explicitly, but not return a handle to that memory. You then go through your process, and then you'd have to free that memory. Whereas now, with the new stuff, you initialize things, you get the sizes, you initialize the structures, and then you do the process. So putting that together, okay, it would look like this. So I've cut bits out of this, but just to get the idea across. So we've got the three calls we just looked at, the FIR get size, the FIR init, and the FIR process itself. And in between these, we've actually explicitly allocated memory for the various buffers themselves. Okay, and in this case, we've defined a length of a kiloword, and taps are being 8. Taps being the number of elements in the weights. And again, that's quite small. The data I kind of work with, even the cut down data sets are of the order of a couple hundred megabytes binary. And the tap size is about 17,000. So this library is not going to be applicable to that environment. What that does is actually it allows me to put a very fine bandpass filter on the data. Anyway, so all the points I'm trying to get here is, here we've calculated some things, the size and the buffer that we need. We've then actually allocated some stuff down here, and then we've passed that stuff back into the actual routine. Also, we've initialized things. Okay. And you notice all these IPPs, malloc things, they almost certainly are doing word alignments on the data. So, okay, so the other major change is that there isn't, in the IPP libraries, there isn't any threading anymore, okay? This is a bit of pseudocode to just kind of illustrate that if you want to have a threaded model, then you're going to have to explicitly thread it yourself here and here using your OpenMP pragma. Okay, and here all we're doing is we're just splitting up the data so that it will actually do the various chunks on the various threads. As I say, it's more or less pseudocode, and I think that's an error there. That shouldn't be there. That should be uncommented. There are a lot of examples online, and it does actually come with a lot of examples as well, so that you can actually just pull things out and run with it. As I say, Intel's taken the policy of getting rid of the big complex examples and favouring the much smaller cut and paste ones. So you can actually find things and easily reproduce results or produce results. Legacy archive, there's no support. That's because they've shifted from the previous internal memory architectures and the previous threading architectures to having those under explicit user control now. So what that means is that, so on the other thing is we've got loads of new examples on the FFT, threading for MIC, examples of the Quark and the Android. Okay, Intel and OpenCV, what's the difference? What's the similarity? There is actually overlap between the two. The major difference is that the IPP provides a high-performance, low-level routine, whereas the OpenCV is, in fact, actually a high-level API. How do you choose which, if you want to use it? You can actually sit OpenCV on top of IPP, and you can actually do that by either, well, you can actually just either explicitly call a library, if it's under Windows, for instance, or Linux, or if it's a part of the cluster stuff, it should actually automatically find it, okay, and use the IPP libraries. You can actually swap out your IPP libraries and use third parties if you wish. But again, as I said, if you're running on a processor that doesn't support IPP, or the actual extensions, the SSE and the AVX, it will actually switch into a software mode. Okay, again, this is very, very brief. It's very messy as a slide. The stuff in light blue, these things are covered by IPP, and the stuff in yellow are covered by OpenCV. So you have various function areas, and as I said, there's quite a lot of overlap between the two, and you can sit OpenCV on top of IPP. So you can also build your Unix-like tools, gzip, for instance, or zlib or whatever. And I don't know how many processors this was, but that one I think was 4. So it's just a quick comparison of an IPP-enabled gzip to an ordinary to an original gzip. Okay, and in terms of speed up and decompression. So on the second image there, I think there are 4 cores, because I couldn't actually translate what that thing up there, and I think it says 4 threads, but me and Windows, me and PowerPoint don't get on that well. The MKL and IPP, both the MKL and the IPP are optimized. Again, they're essentially future-proofed in the sense that you just bind it to a new library. The API shouldn't change now, so that should be okay. There is a major difference between the size of problem for the MKL. That's the math kernel library, by the way. And also, MK is suitable for Fortran programs. Okay. And IPP is specifically designed for smaller systems. I'm going to have to call it quits in a minute. These are the general functional areas. So there is some level of overlap between them, but the target area for the MKL is literally the mathematical applications, engineering, science, and financial markets. Both the library structure and linkage models, although they're both the same thing, they're static, dynamic, or custom. I don't actually know what custom means. Okay, so in the IPP is essentially designed towards the media and communications applications, including speech. Very briefly then, IPP are highly optimized, certainly for the SSE and the AVX. IPP enables you to code now. If you need to, it's future-proof by simply you need a rebuild with the latest version of the IPP and it should be fine. It also saves you time and development because it has this dispatch model whereby you can actually just compile once and deploy many. You can also redistribute it with unlimited copies of runtime library, so there's no cost involved there. There are thousands, as I said, of IPP functions that you can use. And there's also literally a jumpstart sample code that you can use. Oops. So finally, it's part of the Intel Parallel Studio, System Studio, Integrated Native Developer. Okay. Oh, I didn't have to race. Okay. Thank you. Any questions? Oh, sorry.